So the beginning of chapter 11 has some general characteristics that you might find acids and bases. Within foods, anything that has a tangy or sour taste has some kind of weak acid in it. In vinegar, acetic acid. Some stronger acids are the hydrochloric acid in your stomach to help break down foods. So there are a lot of acids in your everyday life. Bases have different physical characteristics. Usually you don't find them as much in foods, more like soaps. They have bitter tastes and slippery feels. A lot of cleaners have sodium hydroxide in it. There are a couple different ways to define acids and bases. Acids are compounds that produce hydrogen ions when they are dissolved in water. And the Arrhenius definition of bases is that they produce hydroxide ions when dissolved in water. We'll see another definition in just a moment. If we dissolve hydrogen bromide gas, let's say it's a gas, and we dissolve it in water, then that is called hydrobromic acid, which is a strong acid. It completely dissociates into ions when it is in water. And since the ion that it gives off is a hydrogen ion, not a hydroxide ion, this would be classified as an acid. Ammonium hydroxide dissolved in water is a mixture of the ions ammonium and hydroxide, making it a base. Anything with a hydroxide ion as part of its formula would be a base. Here we have nitrous acid. Again, it has that hydrogen ion as part of the formula and the word acid as part of the name. And lithium hydroxide, again with a hydroxide ion as part of the formula, is another strong base. Let's take a look at a different definition of acids and bases. It's similar. The acids are a hydrogen ion donor, and so that is the same with the Arrhenius definition, that it gives off a hydrogen ion. And then bases can take a proton. So hydroxide-containing bases definitely accept a proton, but there are other weak bases especially that do accept a proton even though they don't have a hydroxide as part of their formula. For instance, ammonia itself is a base, but it does not have hydroxide as part of its formula. It can, however, accept a proton. Going from ammonia to ammonium ion, what's happening to the ammonia is that it is gaining a hydrogen ion, taking on a proton. It accepts a proton. That's what a base does. It accepts a proton. Going in the other direction, because we see this is a reversible reaction, going from ammonium to ammonia, it is donating or losing a hydrogen ion. So since ammonia is a proton acceptor, that makes it a base. So ammonia is a base, but the ammonium ion is an acid because it can donate a proton. Again, this is a reversible process, so it goes back and forth. Water, in this particular reaction, going in this direction, it is giving up a hydrogen ion. The water is giving a hydrogen ion to the ammonia, so it is donating a hydrogen ion. That makes that an acid. Water in this reaction is acting as an acid. Going in the opposite direction, the hydroxide ion is taking on a hydrogen ion, which is also called a proton. And so the hydroxide ion, as we said before, is a base. So let me just talk a little bit about the use of the word proton. I do like to use the word proton. If you think of a hydrogen atom, it is a proton in the nucleus and one electron outside the nucleus in the electron cloud. So this is a hydrogen atom. If you have a hydrogen ion, it has lost the electron, and so all it is a proton with one positive charge. So that's what a hydrogen ion is. It's actually just one proton. And for me, it's easier to just talk about protons going back and forth. But just remember that a proton is written as hydrogen with a +1 charge in these acid-base equations. All right, so before we do the next one, I wanted to point out these two definitions. Once an acid, so here's our acid here in this equation, once the acid water has lost the proton, what results, the hydroxide ion, is now a base. So we can call that the conjugate base. And the reason it's a base is because going in the opposite direction, it's taking the proton back. And that's what bases do. They take a proton. So we have a giving of a proton, and then we end up with something that can take back the proton. On the other hand, a base, once it has gained a proton, now can act as an acid by giving it up again. Okay, so it's kind of like borrowing and lending money. Let's make you the generous person, the acid. So if you have some money and a friend needs to borrow some money for lunch, you can donate or lend the money to that friend. So you can donate your money, say, okay, well, I have $10, there you go. You can buy a little bit of lunch maybe with that and lend your friend $10. But if that was all the money you had, now you don't have any money. Now you're going to have to go borrow money if you want lunch. Maybe you'll take $5 back or something. I don't know. But so once you've donated some money, once you've lent something, then you can be a borrower. Once you borrow some money, if you're a friend that has to borrow money, now you have some money, now you can help someone else out by donating. So that's kind of how it works. So here we have hydrocyanic acid or hydrogen cyanide, and it is becoming a cyanide ion. The cyanide ion has a sodium next to it because you can't just have an ion hanging around in solution with nothing next to it. But let's go ahead and ignore the sodium for now because we want to focus on what's happening to the proton from an acid-base point of view. So sodium acetate is a source of acetate ion. That's what we have here. And this sodium cyanide is a source of cyanide ion. You can't just get a bottle of acetate ion. If you want acetate ion in your solution, you need to find some sodium acetate or potassium acetate or something else. You can't just get acetate ion because it's negatively charged. All right, so with this HCN going to CN minus, what's happening here is the donation of a proton. So going in this direction, HCN going to CN minus, we have donating a proton. Going the other direction, when cyanide ion goes back to HCN, what's happening is that it's gaining a proton. So the cyanide ion is the base, the hydrocyanic acid is the acid. The acetate ion going to acetic acid involves gaining a proton. So the acetate ion is the base. Going in the reverse direction, acetic acid going to acetate is donating a proton. And so acetic acid is the acid. So we have an acid going to be its conjugate base. The base would become the conjugate acid. Here we have a base becoming a conjugate acid. This acid can become the conjugate base. All right, so those reactions got a little bit crowded with me marking them up all over the place. Let's just take a closer look at just one substance and write the conjugate acid of it. So if we want to write the conjugate acid of this compound must be a base, because what happens to a base is that you have to have it gain one proton and then it becomes the conjugate acid. So in order to make ammonia into the conjugate acid, we have to give it a proton. So we'll change the 3 to a 4. Instead of NH3, we have NH4. And then we have to increase the charge by 1. So that's what we're doing here. We're taking the base and giving it a proton. So to write the conjugate acid, we're adding an H. Usually it's the front of the formula, but for an amine, you put it next to the nitrogen. That's just the way that we draw those formulas. So usually it's the front of the formula, but if it's an amine, it would go after the N. And then once you've increased the number of H's, you also increase the charge by 1. That's what we did here. We increased the number of H's and we increased the charge by 1. So to make this base into its conjugate acid, we have to add a proton. This is not an amine, so we do put the H at the front. And then we increase the charge by 1. So instead of having a -1 charge, this now has a 0 charge, which we don't have to write. So here we have some acids that we want to write the conjugate base of. So if we want to write the conjugate base of something, that something must be acting as an acid. And to get to the conjugate base, we're going to take away a proton. So we take away an H and we reduce the charge by 1. So what an acid does is give away a proton. So we're giving away an H and we're giving away a charge. So that would result in a hydroxide ion for water. One of the H's is missing. The charge has gone down by 1. And for hydrocyanic acid, it would be the cyanide ion. We take away the H and we take away 1. So we're starting with 0. It becomes a -1. The things that we have just drawn are conjugate acid-base pairs. So it's the same species before and after losing a proton. The acid before it loses a proton and the base after it loses a proton would be a conjugate acid-base pair. So let's go back to problem 11.2.1 and identify the conjugate acid-base pairs. So ammonia, we're going to pair it with the same species after it has either gained or lost a proton. So ammonia and ammonium ion, these are a pair. We don't want to pair the ammonia with water or with hydroxide or anything like that. This is the same species before and after donating a proton. Here, going this way, it's gained a proton. Going this way, it's lost a proton. But these two go together. The other pair is the water and the hydroxide. Water and hydroxide are a conjugate acid-base pair. It's the same species before and after losing a proton. Similarly, hydrocyanic acid and cyanide ion are a conjugate acid-base pair. We just did that in the problem below. And acetate and acetic acid are a conjugate acid-base pair because they're the same species with just a proton being different between them. The acetic acid has the proton, the acetate has lost the proton, but they're the same species before and after. Okay, there are some species that can act either as an acid or as a base. I have a couple of examples here. So water can actually act as a base by gaining a proton, or it can act as an acid by losing a proton. So let's see if we can write the conjugate acid of water and the conjugate base of water. I think we've done the conjugate base already. So when it's lost a proton, we have an H missing and we have the charge going down by 1. Water can also gain a proton. So in fact, if there's any protons being given off by acids and water's around, the protons pretty much stick to the water molecules. I like to write a proton just floating around in water like this, but you will find that there are some textbooks that never like to write just the proton alone. They always will write the hydronium ion is what this is called. So they'll write any protons as just being stuck to a water molecule existing as H3O+. Okay, so besides water, there are some other species that can act as an acid or as a base. So we have the bicarbonate ion here as one of those. It can act as a base and it can gain a proton. So if we add a proton here, we're going to increase the number of H's. We'll just make this a 2. And then we're going to increase the charge by 1. So this would be H2CO3, which is carbonic acid. So when bicarbonate gains a proton, it becomes carbonic acid. Bicarbonate can also act as an acid and lose a proton. It does still have a proton that can be lost. That would make it the carbonate ion. We are losing an H, so we just have the CO3, and we are making the charge go down from -1 to -2. So the conjugate base of bicarbonate ion is carbonate ion. So be sure that when you are doing this and getting the conjugate acid or the conjugate base of something, that you only lose one proton. So some acids that have lots of protons, here we go, phosphoric acid, if we want to write the conjugate base of that, we would just lose one of these protons. So we're going to keep 2. So the conjugate base of phosphoric acid is the dihydrogen phosphate ion, not the phosphate ion and not the hydrogen phosphate ion. It will be the dihydrogen phosphate ion. So this is another one of those species that can be amphoteric. It can either have a conjugate acid. So looking at the dihydrogen phosphate ion, phosphoric acid is the conjugate acid of that. And the conjugate base of the dihydrogen phosphate, now we're starting to talk about this as if this is the middle thing here. So the conjugate acid of dihydrogen phosphate would be phosphoric acid, gaining 1 proton. The conjugate base of dihydrogen phosphate would be hydrogen phosphate, not just the phosphate ion. We're just going to lose 1 proton. So whenever you do this, just remember to do one at a time. So we have the conjugate base of the dihydrogen phosphate being hydrogen phosphate, and the conjugate acid of dihydrogen phosphate being phosphoric acid. So remember, when you do the conjugate acid or base of something, only work with 1 proton at a time, even though we do have these species that can go several steps in each direction.